Yeah, everyone, welcome to the video. What we're going to be looking at today is the graphs of y equals log base a of x. Um, and not too complicated, I'd say. Definitely not as complicated as trig graphs or anything like that. But some people you can get a little bit hairy because of the base a. People get a little bit confused, but the base a doesn't really have a massive effect on what the graph looks like. So let's just have a look at it. So firstly, let's just have a think about a few different points. Firstly, what happens when y is equal to 0? So when y is equal to 0, let's just have a look at, so 0 is equal to log a of x. And so if we rewrite this, that means that the a to the power 0 is equal to x, and we know that a to the power 0 is 1, and so x is equal to 1. And so that means that doesn't matter what the point A is, that every single graph of log base AX will go through 1, 0. Oh, I always do that. Will always go through 1, 0. So that's the first really important point that this thing will go through. The other important point that it will go through is when in particular that you've got when x is equal to a. Okay, so when x is equal to a, let's have a look at the next one. When x is equal to a, then y will be equal to log a of a, and a to the a, the power there is equal to 1, and so a to the power a is equal to 1, log a to the a, and so therefore the point a1 will always be on the graph also. Okay, so they're the sort of the two key points that we're always going to know. What will happen, let's just have a look at it again before we sort of draw what the graph actually looks like. Log a to the x. As x gets bigger and bigger, then a to the power of something must equal x. And so that something is also going to get bigger to make that true. Okay, so if I just rewrite that, then, a to the power y is equal to x. What y value do you need to make that true? As x gets bigger and bigger, then y gets bigger, but it doesn't get bigger as fast, if that sort of makes sense. And so the graph sort of peters out. It flattens out. It doesn't keep increasing quickly. And as x gets less than 1, so here we've got x is equal to 1, 0. If x is less than 1, then the log of ax gets smaller and smaller. In fact, it becomes negative because you want negative powers to make fractions. And so it goes out. That wasn't a very good explanation. Definitely not my best explanation of what the thing looks like, but what does it actually look like? So if we have our graph here, then we know we've got our point. It always is going to cross at 1, 0. It's going to go through that. It's always going to go through the point A1. And the graph looks like this. So what happens is that it goes through that. Like I said, it sort of increases and gets there, but it sort of peters out. It goes across like that because what we're talking about is what power is required to equal that, and the power needs to be less and less to keep going for that value of x. Hope that sort of makes sense. And we also said that once we get negative powers, that makes the value get less and less, but never gets equal to 0. So it gets closer and closer to 0, but never actually quite equals 0. So that is actually an asymptote. It will never equal 0. If you think about it, x can never equal 0 here. We've spoken about that before. It can never hit that line because a to the power of something can never equal 0. It'll always be there. So we're going to get an asymptote at x equals 0. It's going to go through the point 1, 0. And it's going to go through point A1. And they're all my important sort of features of the graph of log AX. Hope that makes sense. Let's try sketching some. Maybe we'll just write down the domain and range just to sort of make it complete. What's the domain? Well, it goes from 0 to infinity. And what's the range? The range is all real values. It keeps increasing forever. It just increases at a slower rate as x gets bigger and bigger. Okay, very, very good. Let's try to sketch some of these suckers. Okay, so we've got log equals y e x plus 3 minus 1. So what is this? Firstly, what does this plus 3 do? That plus 3 means it moves to the left. That's supposed to be a arrow to the left. It goes 3 units to the left. And that -1, what does that mean? And it goes down by 1. Okay, and so that's all we have to do. If we think about the original graph, what's going to happen is that asymptote is going to move 3 spots to the left, and all those 2 other points are just going to move 1 space down. Okay, so the y value will go 1 down. A is equal to E here, and so E is our special Euler's constant there, and so Euler's number, whatever you want to say it. So let's have a think about this. So the original graph, I'll just sort of show you how I think about it. So the original graph looks like this. So that's y equals e to the power x. Just draw that again. That was pretty gross. Y equals e to the x goes through 1, 0, and it also goes through, remembering what we had before, here it goes through the point A1, so this goes through the point E1. E1. So it goes through 2 points. So that's the graph of log EX, okay, y equals log EX. And what's going to happen is it's going to move to the left by 3 and up by 1. So what, I forgot to put in my asymptote there, so you got asymptote down there. At x equals 0. So what we're going to have now is an asymptote at x equals -3. The graph's going to sort of come up, and what's going to happen, because this original graph, because that goes through the point 1, 0, it goes through that point 1, 0, if it moves to the left, it's going to go through the point -2, 0. So we know that's going to cross at -2 here. Okay, so that'll be -2. It's going to go through that point -2, 0. Okay, goes through that point because it's moved to the left by 3. So that's what it will look like. And if we want to do the E point as well, E1, if it moves to the left, we won't do that for the moment. Okay, well, sure, we can do it. So if that moves to the left, then it's going to be, if it moves to the left, it's going to be E, take away 3, 1. Okay, so that's just taken in, there's just moving everything to the left by 3. Okay, but then we also need to move it down. Okay, so we'll move this sucker down. Okay, and so what does that look like? I'll probably just go, I won't go straight to my graph yet. I'll just have a look at it. Then, so that's just applying the left by 3. And then if we apply moving it all down, still going to have asymptote of -3. That will not change. But my y values are going to drop down by 1. So it's going to now, instead of going through -2, 0, it's going to go through the point -2, -1. So here, -2, -1, that point there. And it's going to go through, instead of E minus 3, take away 1, it'll be E minus 3, 0, because that y value is going down. So that's actually going to give us a nice little y-intercept there. Sorry, x-intercept, E minus 3. And so that's actually going to be about there. Oh, I'm still on highlighter. It's going to be about there. And that will be the point E minus 3, 0. It's going to go through there, and the graph's going to come up like that. Okay, so I mean, I'm just sort of sketching it on here, but so the finished graph will look like x equals -3. It's going to go through the point -2, 1, -1, so there, and it's going to go through the point here of, never know where to draw these things, E minus 3, which is slightly negative because E is 2.7 something. That point there, and so it comes up and goes like that. Okay, so that's the graph of y equals log EX plus 3. Now, I just sort of did that all by just sort of moving the points all over the place. You could equally just go and find, it's really easy to find this 1, 0 point. You go, well, it moves to the left by 3, down by 1, etc., etc. You can also just solve x, y, and intercepts. You could equally do that to get an idea of what the graph is and know that the asymptote is there. So that would be a probably faster way to doing it in this, but it's really important to understand transformations to be sort of successful in this subject. Hope that makes sense. Let's have a look at one more just to have a sort of bit of an idea about what's going on with these graphs. So last one. So let's have a think about this. What's happening here? So we've got y equals 2 log e3x. So just quickly, so the original graph looks like this. Y equals log ex looks like that. Again, going through 1, 0. Again, going through E1. And then what happens to it? Okay, so firstly, what does this 2 do? That 2 stretches everything in the y out by, it doubles everything on the y from the x-axis. So I'm just going to sort of play around with these things. So that's going to be, I'm going to go a bit quicker here. So that'll stretch out this E, instead of E1, that'll be E2. It doubles. It's sort of getting stretched out that way. This y value here does not change, because it's getting stretched out from the x-axis. So that doesn't change. So we've got that. It just becomes E2. What does this 3 in front of the x, what does that 3 do? Well, yeah, let's just do that one first. That's going to compress everything from the y-axis by a factor of 3. And so what that's going to do is all the x values are going to be divided by 3. So that will be E over 3, and that's going to be 1 over 3. Okay, so that's going to compress that in by a factor of 3, and so we've got those 2 points. And lastly, we've got this negative in front of the x that flips it, that reflects it in the y-axis, and so it's going to flip all across. So that's going to become over this way. So it's going to instead look like this, like that. And so my x values are going to become negative. So it's going to become negative 1/3 0. Negative 1/3 0. Oh, this might be my final graph. Let's just cut it short for this one because there's no point going on. And then negative E over 3, 2. And so that's what my final graph will look like for that. So that's just applying sort of transformation rules. So you can sort of play around with those and get like a quick graph done about what it looks like. Hope that makes sense. I'll see you in the next video.